Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Good morning, everyone. It's my pleasure to introduce Max Krohn from MIT. Max is a PhD candidate. He has been working with advisors Franz and Robert. He also manages a number of startups throughout his PhD program. And today he's going to tell us about his dissertation work on securing the web with decentralized information flow control.
All right. Thanks, Helen, and thanks for inviting me today. As we all know, there's a computing shift going on, that we've been using our PCs for the last 10 years or so, 20 years, to both store our files and also run computations on those files. But of course, as we become all more interested with the web and comfortable with using it, we're now uploading our files onto those websites and now using those websites to run computations on those websites that we used to run on our PCs. And a lot of companies are getting into this act. If you ask Google, they're going to replace Microsoft Office with their Google version of the Office suite. And there are other debatable, but I'm sure you've all tried to use it. It's not there yet. But
by the way, it's not a PC, it's a Mac.
and there are other companies like Facebook that are getting in on this act too. So what are the security implications of changing the way we do these computations? Well, the first thing to realize is that a lot of these new websites are just supersets of the old. And as such, they're susceptible to all the same attacks. And so here's this first attack that I call the classic attack, where you have a bad guy like Bob, and he's going after the data that's stored in this web application. So Alice's data and Bob's data is both stored in the server. What Bob will do is he'll generate some kind of malicious link. It'll trigger some bug in the web application. And before you know it, the web application is now willing to send him Alice's data. So once Bob does this for Alice, he does it for everyone else on the rest of on the database, and he has his own copy of the server's database to do with as he pleases. And this is not an academic problem. As we've all known, these cases come up all the time in the popular press. There are some interesting ones within the last couple of months or so. Harvard had its graduate student application data breached, and also Facebook, which is known for its great security properties, had a pretty serious lapse with who they're willing to show photos to. So these are problems with web applications of the past, and there's still going to be problems in the future. But as these web applications turn to something bigger and better, there are new types of attacks that are coming into focus. And this is what I call server-side malware. And I'm going to use the Facebook as an example here, but a lot of other websites will have the same problem. And so in 2004, when Facebook first started up, it was structured like any other website. Alice would make a request for feature A. Feature A was implemented by the Facebook developers. They got it right. They made sure not to send Alice Bob's data. But about a year ago, they tried something pretty interesting, where they said, let's not be in the business of making all these applications ourselves. Let's try to outsource some of this work and potentially some of the benefit to these willing third-party volunteers. So if you go to Facebook now, if Alice goes to Facebook, she'll issue a request for feature C. What Facebook will do is it'll send that request via some XML RPC to another server across the internet. And when that server is trying to make some response to send back to Alice, it'll have access to Alice's data that's stored on Facebook. And it'll generate some response and send it back to her. Of course, we might be wondering what happens if this third-party application is malicious. If its only goal in life is just to steal Alice's data. And there's really nothing in the Facebook model to prevent this from happening. And what's really interesting is this is really the same malware problem that we've had in our desktops all along. It's now jumped onto the server side. And it's the same problem. The same broken solutions are being applied. This is the way we used to solve the malware problem on our desktop. Obviously, this isn't really working. And Facebook has the same thing on their server. You just have to authorize this application to use your data. But of course, this is not a very easy decision for a lot of people to make. So it seems like we've gone from bad to worse. That the websites that we use have always had this problem of these security vulnerabilities allowing attackers to steal data. And now this whole malware problem has jumped onto the server as well. And there are other attacks that you might be thinking of that we're not going to consider in this talk, like cross-site scripting and phishing, and they're important, but they're just not going to be on today's menu. So what can we do? I think one approach is just to not use the web and retreat to our underground bunker. And this is the pessimistic view of the world. But this is actually, in another way, is a very compelling opportunity for systems developers. Because in a way, we're changing the way people are doing their work. We don't have to deal with a lot of the legacy issues that we have that come with changing the desktop. So this might be a good time to build new systems. And we're going to go with the first approach, and I will stop early. No. We're going to try to build new systems. So we'll see what that looks like. OK, so my work as a grad student has been mainly trying to build secure websites. And I started off, as Helen was saying, in the private space where I was making involved with startups where there were people like Bob trying to steal our data. We had to do our best job to secure it. But as I've been in grad school, I've been trying to think about more general approaches to these same types of problems. And that's what I'll be presenting today. In particular, I'll be talking about the last two papers in this sequence, one about a new operating system called Flume, another about new ideas for the future web, things like Facebook applications. So let's zoom in a little bit and figure out why this is a hard problem. So here's my schematic diagram of what a website looks like. There's some off-the-shelf database, there's some web server, and in between there's a whole bunch of code that's specific to the particular website that's running the application. So in this case, it could be written in lots of different languages. A lot of times they're big distributed systems spread across multiple machines. And what makes this difficult is that if there's a bug in any one of these components, that might be enough for somebody like Bob to break in and steal data. And moreover, as these systems get more mature, we have to think about what happens when somebody like Bob can actually insert his code directly into this blob of stuff that has to be correct in order for security properties to be upheld. So the approach we're going to take today is to treat as much of this stuff as possible as a black box. And that is to know that there are some inputs to this black box, to rely upon some very automated mechanism to track data as it flows through the black box, and then to put all of our security decisions into this isolated module, which I have now called the gateway. And the idea being that if you want to audit that the system is secure, you can focus all your efforts on the gateway and not have to worry about the black box. So if we think about what this black box is going to look like and how the automated mechanism is going to track what's in it, the first decision we have to make is, are we thinking about a compile time or a runtime mechanism? And in my experience, I think that websites tend to favor runtime tracking. And I know that with the Singularity project, there's been a lot of great progress in making compile time checks more feasible. But I'm going to take the point of view that runtime tracking is the way to go in the case of large websites, particularly because a lot of these depend on these very poorly defined scripting languages that are hard to model in terms of static checking, and also because with incremental deployment and things being need to roll out at a very fast pace in a lot of cases, it's not always the case we could take down the whole website, check in, and then roll it back out again. So there are a lot of problems with getting a compile time system working here. So in particular, we're going to try to focus on what if the tracking mechanism is runtime for the purposes of this paper. And the general solution that we have is the OS tracking the data inside the black box at runtime and pushing all the security decisions into an isolated module, this gateway module. And this is called decentralized information flow for the operating system. And we've invented it more or less anew to solve this problem. And we should point out that it used to be a PL-based idea in the late 90s, and it's inspired our work, but we've done a lot of additional work to get it working for the operating system. So just to focus on what's actually going to be covered today, the overall idea is that of end-to-end web security as I described it. Not worrying about what's in the black box, just pushing as much of our security decisions to the ends of the system as possible. To realize that we had to build a new operating system, one built this technology called Decentralized Information Flow Control, meaning we had to make a new model for DIFC at the OS level. We had to specify an API to make it possible to build applications like web applications. We implemented on 2 different operating systems, Linux and OpenBSD. And finally, we have a case study of a real application that we secured using our new system. And finally, at the end of the talk, we'll get to generalizations of this idea in terms of how to build new websites like Facebook. Question?
So maybe I'm misreading this, but end-to-end web security sounds to me like something that involves the client as well as the channel.
Okay, that's a great question. So if you start thinking about the client, then you're probably thinking more about things like cross-site scripting or
Not necessarily.
okay. So let me just say that I agree with you, but I think we're just end-to-end in terms of what's on the server for our talk today. If we could, we'd change the clients too and bring it into this model as well. But we haven't done that. Okay. Yeah. All right. That's certainly true. I agree. Okay. And the outline is we'll just cover these read points, these high-level points. First, what we did to the OS to support these new this new model, then our experience with an application, and then this generalization. Okay, so now I'm going to jump into what this diffc idea is by an example. So you can imagine a website. In this case, here's Alice. The web application is now split into two different pieces. One, the web app that does most of the work, and then also this gateway that's going to do all the security decisions. And if you look at this website, there are two different files. One is Alice's data file, one is Bob's. And the kernel has some understanding of some tagging mechanism whereby it knows that Alice's is Alice's and Bob's is Bob's. And finally, we've changed the kernel, so it's not a standard kernel, it's a diffc kernel. So when Alice comes to the website and she wants to get her data off, what's going to happen is the web application is going to read Alice's file. And as it does so, the kernel is going to make some annotation that says, oh, this web app has read Alice's file. That way, when the web application tries to send that data out to the network, it has to go through this gateway process. And the gateway will know that this web application might have done a lot of things, but I know for a fact that it's read Alice's data. And then the gateway can make the decision to send the data to Alice and not to Bob. And the OS is not going to enforce that decision. It's going to be up to the gateway to get that right. So there are three different parts that I need to describe in more detail. The first is how to go about labeling secret data. You have Bob's data, Alice's data, or there are other types of data possible. Also, how is the kernel tracking the data as processes read files and write to other processes? And finally, how is the gateway able to legislate some kind of reasonable security policy? And so you can think about a division of powers here where the kernel is really in charge of the enforcement of some policy, and some applications like the gateway are able to legislate it. So we'll hit those 3 points in order. So the first is how to label data. And on our system, each processor file is going to get what's called a secrecy label assigned to it or attached to it by the kernel. And what a secrecy label is it's a summary of all the different types of secret data that a processor file is assumed to have been influenced by. So for example, secrecy labels are of the form, this is Alice's secret data, this is Bob's secret data, or, oh, potentially, here's a file with financial secrets, or this process has seen both financial secrets and Alice's data. So we're going to call these individual categories tags, and collections of these are just going to be called labels. And each file or process is going to have a label. Okay, that's how to tag data, how to label data. The next question is how the enforcement is going to work. What types of data flow is going to be allowed inside the system? And there are two basic rules for this. The first is that if there's ever a process on the system that has a non-empty secrecy label, then it's not going to be allowed to speak to the network, which means that a process can't read a file and then broadcast it to the whole net. And the second rule has to do with how data is allowed to flow in the system. So there's a process P and another process Q. Potentially P is a process and Q is a file, or vice versa. The kernel is only going to allow communication from P to Q if P's secrecy label is a subset of Q's secrecy label. So I'll show you in this example why that makes sense. You can imagine there's some web application that's seen both Alice and Bob's data. So its label is A and B. And there's some file that only has Alice's data. So its label is A. So what the kernel is going to do is it's going to allow the web application to read that file by application of the subset rule. And the justification is that there's nothing the web app can read or can gain from reading that file that it couldn't have already known with its label the way it is. On the other hand, the kernel is going to disallow that application from actually writing to the file. Because if the kernel were to allow it, it would allow the web application to feed information about Bob's data into this file that's only labeled to accommodate Alice's data. So that's just both directions of the subset rule. And you can apply it to other cases as well. You can imagine two different processes. Here's the web application and the helper process. And in this case, they have incomparable labels, meaning neither is a subset of the other, so the kernel is going to disallow communication in both directions. OK, so that's 2 down. We have how to label secret data, how to track secret data. And the final thing is how processes like the gateway are going to be able to legislate policy. And we could split this into 3 different sub-bullets. The first is going to be that processes of any sort on the system are going to be allowed to add tags into their secrecy label as they want to. There's going to be no restriction on that. The second is that some processes, or all processes can allocate tags. And the third is that some processes are going to be able to change their labels by subtracting tags. So we'll hit all 3 of those now. So imagine the web application starts off with an empty secrecy label and wants to do something like read Bob's data. So it could ask the kernel, please change my label to have this tag B in it, and the kernel will say, sure, that's fine with me. It will not allow the application to go in the other direction and to subtract that tag B from its label. So in some sense, this is a one-way operation. Yes?
Why did it even need to ask for the label? Like, wouldn't it satisfy the subset relationship even without that?
Why would it, in other words, why does it have to ask the kernel explicitly, please change my label?
Yeah.
Well, that's a great question. A lot of the systems in the literature, the classic Mac systems, allow for dynamic label change. There's a deep reason why that leaks information. And I could try to set up the whole example for you. It'll take a couple minutes, but
Yeah, that's fine.
OK. But I could bring. It's really interesting, but it's
Basically, that if you could have information leak because you'd know whether you could read the data or not, right? So if you were denied access, that would leak data. Whereas if you have to ask before, then
that's a good way to describe it. That if you access data and all of a sudden your label has changed, then you've gained information. Now you can decide not to communicate with somebody, and that's a bit of information right there. Yeah, great. So you have to know how to change your label.
Obviously, if you try to read it, it says no, that's conveying information to you.
Right.
But
So how do you know what the label is in order to change what your label?
The point is that the difference is that the information that's conveyed to you in your instance is just that my label set was incompatible, and in the other instance, it tells you what the label set was, at the cost of upgrading your tags.
Right. I would agree with that, more or less. OK. These are good questions. Yeah.
is this channel even exploitable to like learn useful information?
Yes. It can. I could. So this is an example that I have at the end of the talk. I mean, sorry, in the backup slides. It's interesting, but it might derail us a little bit if we do it. But yes, it is. And for a while, people thought in the 70s, people thought dynamic label changes were a bad idea because of this reason. So we've known about it for a while. And I think for that reason, all this stuff started going the language direction because you could check at compile time, more or less, a lot of these same decisions. And therefore, you remove that channel to dynamic label change. But I think with this set of API, I think we've introduced the idea of explicit label changes, which actually was first introduced by Highstar a year before this work. But that's going to solve that channel you're worried about. Ed?
Here's the applications that come with log a lot of information to disk.
Yeah.
And those log files will generally have a subset, I would assume, of the labels that the application does, because the application's reading lots of files in, wants to log it out. Does the log file have to have the same?
So there are multiple ways of doing this. It would be nice to say that any process can open a file append only and just stick information in it. And you can imagine a file with a very big label that has every tag on the system in it, and everyone can write to it, is one way of doing it. We haven't got the way to exactly get real append-only semantics in our implementation without being able to leak data back to the. So we are enforcing that basically to open a file, to write to it in any way, you have to have an equal label as the file. However, if you really want to make a logger, one of the best ways to do it would be to have a privileged process, which we'll get to in a couple of slides, and you just trust that logger to only write in one direction. Seems like a pretty easy process to write. So that's a good question, too. Yeah, Kim.
Drill in a little details, because in abstract, I guess about 2 slides where you had communicating with the file,
Right.
actually communicating with the file system, right? And so in the abstract communication, talking about data flowing only one direction makes sense. But I guess in the concrete, I guess what I'm asking is, are you going to come back and explain to me like why the input parameters to the file read request that have data, why that is not a transfer of information?
Right. I'm not going to explain that to you. I'm just trying to come up with the right answer. So the first thing that I'm not telling you is how a process is able to change its label in the right direction, because it has to be able to read the label in the file first before it knows how to change it, and then only after that can it read it. So one answer there is we're setting up the file system where the labels are hierarchically decreasing as you go down. So the root will have an empty label, and way down you'll have a file with A, B, C, D, E, F, G. And you could go almost stepwise down the file system, and at each step add another tag until you eventually got to the right label for you to open this file. In terms of the open call itself leaking information, I guess my question is, who would you be leaking it to? Would you be leaking it to the kernel? Because the kernel is trusted not to not to allow you to leak information. But
if I think about the way IPC mechanisms tend to work in operating systems,
okay.
there's in fact no way to go home. Almost always IPC is bidirectional.
Oh, this is a great
right?
question. Okay.
Right? I mean, even if, I think of the data is only flowing one way, I'm passing parameters.
Oh,
Who's
okay.
to tell me that my parameter isn't the secret piece of information?
Okay, so that's a great question. And I think this is better explored if you think about IPC. So you mentioned IPC, and even in the case of a one-way Unix pipe, you definitely have information going in the opposite direction in terms of flow control, and when potentially one guy crashed and the other guy will get an EOF. So we're only in our system allowing unidirectional IPC if both processes have the same label. And we have another implementation of real DIFC one-way channel, but that's a very different channel from what you're expecting on Unix. We have a limited buffer. Once you fill up the buffer, you're done. It just falls off the end. Yeah, exactly.
The labeling is on files, right?
Mm-hmm.
So what happens if you have a database where all the files are in one
Okay.
set, and now you need to label for everything?
Let me get to that in a couple slides. You basically need a you need a trusted component to your database is a trusted component. So there'll be one database file that has a tag of X that only the database can see, and it's getting input from lots of different places. It's going to be trusted to internally keep the right tagging mechanism in all the rows in the data, and it's going to be also trusted to apply the right labels as they go out. And so in this whole system, we're not making the problem go away of security. We're just really limiting to where we're thinking about security decisions. So the database is a place we have to worry about security decisions. The gateway is potentially other pieces will be around the periphery that we have to get right. That's all the stuff in the middle that, like the web application, that we don't need to get right. Yes?
So the real-life security break-ins that you showed a few slides back,
Uh-huh.
are they attributed to these
Okay.
subtle issues that you're showing here,
The-
or is it
the-
just SQL injection? Is it something simple?
It's usually SQL injection, but the question is, can you fit those SQL injection attacks into a larger framework? Well, we'll get to that a little bit later.
I think you can, but there are
Yeah.
simple solutions to those.
Absolutely, but they're usually one-off solutions. But we'll get to that later. The Facebook attack was not a SQL injection attack. It was just bad ACL policies at the application level. We'll have a lot more on that. Okay, I'm going to go on to how processes can allocate tags. I don't know. Okay, so think about Alice showing up to this website for the first time. She's never been here before. And the gateway is going to have to come up with some new idea as to what tag should I assign to Alice. So she's going to call into the kernel. She's going to say, please create for me a new tag. And the kernel will give back some token, and the gateway will associate it with its tag A for Alice. As a side effect, it gets this new privilege, this new A tag is added to its declassification label. And let me show you what declassification is. So there are two labels now, one secrecy as before, and the second D for declassification. So this gateway process, like any other process, is allowed to add A into its secrecy label. So it's allowed to ask the kernel, please change my label to have A in it. And now because it has this declassification tag for A, it can ask the kernel to subtract it. And the kernel will actually go ahead and allow that to happen. So having stuff in your declassification label, these are privileges that the operating system is giving to applications, and the applications are trusted to use those privileges correctly. So now we can put all the pieces together and see how this helps in the case of a website scenario. So first, let's go through the case. Yes?
Is
do we need to do something special to declare that the gateway is privileged and is allowed to create the tag? Or is the point that because the gateway created the tag, he can do no harm in declassifying because nobody else can create the same tag?
Exactly the point.
Okay.
Thank you. OK. So what happens when Alice wants to get her data out of the system? So she'll show up. She'll make some requests to the gateway. The gateway will then tell everyone in the system we're about to serve Alice's data, more or less. So what that means is the web application is going to add A into its secrecy label. The gateway is going to add A into its secrecy label. And now if you just apply the subset rule, you can see that Alice's data can go to the web app, and the web app can send data by IPC to the gateway. Now the gateway is going to use its declassification privileges to subtract that A out of its secrecy label, and then send data to Alice, and not to send data to Bob. It's trusted not to do that. So now, let's imagine what happens if Bob is an attacker and he wants to get Alice's data out of the system. And also, let's make the further assumption that, that Bob he knows about some bug on this web application that's going to allow the web application to do whatever he pleases. So we'll make the pessimal assumption. OK, well, the first thing he'll tell the web application is, well, forget about this gateway guy. Just try to send the data directly to me. And in this case, the kernel obviously won't allow that because we said this rule of that processes can only send data out to the network if they have a non-empty secrecy label. So that will have failed. And then Bob will try something else. So he'll tell the web application, well, launch your friend this helper malware process and send Alice's data to the malware process, and then have that application send data out. Well, of course, that application is in the same predicament that the original web application was, that because it received data from the web app, it has to have A in its secrecy label. Once it has A in its label, it can send data out. And if it were to try to route that data through the gateway instead, the gateway is only making this decision based upon the label of the data that came to it. So it'll make the same decision in either case, and it'll know not to send that data to Bob. And the appealing property here is that we can think about a lot of this stuff in this box as a black box. We don't have to reason about it in terms of security. We have to get the gateway right, but not the stuff in the black box. Yes?
So far you've been labeling processes with these tags, but here you suggested that the gateway could know whether this data had label A. Is that?
Well, so the process, so the gateway is going to, I mean, we'll see in a little bit the mechanism for how it knows that, but it just knows that it's communicating with any process, and that the label on other process has an A in it, is what the gateway knows.
I guess
the thing you said earlier that you're enforcing is the subset relationship. But the subset relationship itself can't tell you that the helper malware only has A. Or
Yeah,
that
it could have more than A, but, well.
I mean, what if it has
just B, for example.
OK, well, the gateway, so what had to happen is that the gateway had to set its tag equal to A. And that's the only way it would be able to get information in from these other places.
I see, so the gateway will explicitly set its tag
To A or B,
right.
Receive the information, then drop the
Yeah.
tag.
If the other guy had B, then it would just not be able to communicate with the gateway.
Got it. So it has to explicitly
Say whose data it's accepting by raising its tag.
Absolutely.
Okay.
Yes?
If you want to handle multiple connections concurrently, do you instantiate the gateway?
So we're just assuming all these guys handle one connection and disappear. That's actually pretty close to the way we've implemented it. That's a performance problem. We can talk about performance in a little bit, but we should probably get onto the other stuff. But I certainly agree it's an issue. Yeah.
You're assuming that malicious web apps can be malicious. But you're assuming that they have no covert way of communicating between each other that your tagging system doesn't catch.
Absolutely. So if there are covert channels, then I agree entirely. Then what would happen is this friend application would show up. It would have an empty label. The web application would have A in it. They'd exploit the processor cache in a way that would communicate bits. And
all the old problems that multi-user, multitasking systems used to have to try to prevent the security covert channels.
Absolutely.
So processors using extra CPU time,
Messing with the cache, messing with the TLD.
Absolutely.
Yeah.
Agreed. Yeah. So, I mean, one answer to that, which if you had just two processes running on the machine, I agree that would be a real concern. if you have 1,000 or 100, which a real web server would. Sorry?
Any bad at statistics? I mean, the answer to that is that you have to use statistical methods.
Sure. So it's a much noisier channel, and you're just going to leak fewer information. So, but if you think about these attacks, a lot of times the question is if only one person's account was broken into, it wouldn't be that much of an issue. The problem is that they're leaking the whole contents. Buggy web apps leak the whole contents of the database. And if you're just able to rate limit these attacks to just be whatever you can get through a timing channel, it's much better than if you're the hashes of the passwords, because good web applications should be storing passwords. So this guy's checking the passwords. So you're already assuming he's not doing the right thing. And so he's the one who's going to be sending the hash to someplace else.
The password hash there.
Yeah. So, but you're right. We have not solved timing channels. I agree. Yeah. Yes.
What is the compelling reason to use this MAC-like model instead of a DAC-like model where the gateway simply, after it creates that principal, it gives it to the web app, and then the web app can only read A's data, and then it comes back? And what is that?
Well, so can the web app in your model write a file without, can it write a publicly readable file into the file system? The problem is the DAC policies tend not to be transitive. That you can only make the security decision once, but then the data's out of the bottle once it happens. These policies tend to have these nice transitive property that you could track wherever Alice's data, whatever its influences, as long as there are no timing channels, whatever those influences are in the system. So this is the classic reason why you'd use a MAC approach as opposed to a DAC approach. And you probably can build some kind of crazy capability system where you do solve every single problem, and then you're basically getting back to MAC if you did. OK, let me go on. OK, so we talked about the traditional IFC ideas are certainly at play here. There have been a lot of other OSs that have tried similar approaches, like Bell, Lapadula, Kikos, et cetera. The key difference between our system and those are just these new APIs we've given to programs that they could create tags and change their labels explicitly. And this is really what it takes, in our experience, to get web applications actually running using the system. OK, so now let's focus a little bit on what the right API is for exposing to these applications. And we've already touched on it a little bit. But if you were to go actually build a real OS using this model, what would be the first thing you'd do? Well, probably you'd stick with a regular operating system like Unix and try to maintain as much as possible the existing API, things like files and reliable IPC and network sockets and such, and then add these label rules onto them. Unfortunately, this has been a pretty prickly issue in the past, and a lot of the systems that have done this have not been entirely usable. So we've tried to focus a lot of our efforts on building the simplest abstractions possible in order to merge these diffsy rules with existing Unix-like abstractions. So let me go over some of the reasons why this is difficult. If you can imagine the gateway process, it's really speaking to 3, maybe more different types of counterparties. It's speaking to the web application that has a tag of Alice. It's probably speaking to some password database to check hashes of passwords. And it's also speaking to the network. Think about the way you'd label these different resources. They probably all have different labels. So the question is, what label should the gateway run as? It's non-explicit. It's not entirely clear, especially if the gateway is multi-threaded and running between these, running all 3 of these different communication channels at once. Another gotcha to building a system this way is that it's very easy to build buggy applications. And so you can imagine the gateway was having a very successful conversation with its friend, the web application. Then it got some great idea that, oh, there's some top secret file that I want to go read that I don't have the ability to declassify. Well, then the operating system would allow it to add T into its label in order for it to read that file. But then when it goes to read its pipe from the web application, maybe a minute or so later, all of a sudden this communication channel would have been broken. And from the gateway's perspective, it's pretty mysterious to understand why exactly it can no longer speak to the web application. Did the application crash? Is it just taking a long time to respond, et cetera? So there are a lot of these very subtle issues that come with actually building a system using these types of primitives. So to bridge the gap between the diffC model and the APIs we currently use, we've added a single layer of indirection between the two. We call this endpoints. And what endpoints allow processes to do is that they allow processes to label individually their different resources. So if the gateway has a pipe to the web application, it can put a label of A explicitly on that. And same for these other resources that it happens to be speaking to. And now when the kernel is making decisions as to which processes to allow to communicate, it's going to make those communications based on the labels on the endpoints, not the labels on the processes themselves. So in this case, the web application and the gateway both have their endpoints on this pipe running between them labeled at A. Then the kernel will know that both subsets are upheld and that it's OK to allow regular Unix pipe semantics between these two different endpoints. What's going on here, though, is actually these endpoints are implicitly capturing this idea of declassification. That when data is entering into this gateway process, it's as if the process has a label of A. But it turns out the process is able to keep this overall process label of empty. So it ought to have had the ability to declassify, to both read data that's labeled as A and behave as if it has an empty label. So the kernel is only going to allow this type of configuration if this process has A in its declassification label. And so you can come up with a more general restriction on the configuration of endpoints. That if there are any tags in the processes label that aren't in the endpoints label, they ought to be able, then the process has to have the ability to declassify those tags. And this is just the way that you notate setwise XOR. It's the symmetric difference between those two labels. So this is really a two-way street here, and that the kernel is using this restriction to restrict the way that processes set up their endpoint configurations. But it's also allowing processes to restrict themselves in such a way that they can solve bugs that we previously saw. So if you think about this example of this gateway that was having this very successful communication with its friend, the web application, and then had this bad idea of reading this temporary file that it shouldn't have read. Well, what happens in that scenario is that when the gateway actually tries to introduce this new tag into its label, the kernel is going to say to the gateway, I'm not going to allow you to do that, because if I were to allow you to make that change, then it would invalidate the restriction I placed on this endpoint that you had to the web application. And so here what's happening is that the gateway is able to express the right communication requirements to the kernel, and the kernel is able to return the favor by just telling the gateway when it's doing something that's going to get in the way of those requirements. So this is a very useful abstraction for
You add an endpoint to the top secret file, and the idea is the code that's talking to that endpoint is responsible for doing the correct, for behaving correctly with respect to this declassification.
Yeah, but this process couldn't do that because let's say it didn't have the ability to declassify. In this case, what the process would have to do, it would have to close that communication channel to the web app, and then that endpoint would go away, and then the kernel would allow it to read the file. So it's more or less what you'd want the application programmer to see. Please close this connection before I allow you to read that file. And the interesting thing here is that we haven't introduced any new features into our model, that we have the same exact model that I described to you earlier, but that this endpoint feature just provably fits inside of it. That the kernel is enforcing the right communication between the endpoints and also enforces the right restrictions on how these endpoints are configured, then all processes are obeying the subset rule. It's more or less the result that we have.
Why it's getting a conflict, and it stops you from having to up and down your subset level all the time to classify stuff.
Exactly, and this is especially an issue because a process is getting all sorts of asynchronous messages where, for instance, if it has a pipe open to another process, the control flow is all asynchronous. So it wouldn't be practical because the process wouldn't even know when to do it. So it just allowed it to set a very firm communication discipline for each way it's communicating. Yes?
So does this mean in practice the process secrecy label is fixed for the entire duration?
Yes, unless it wants to read something that it can't declassify. So in the case where it read that secret file, it had to add T into its process-wide secrecy label, and that's then going to affect all the future endpoint configurations it could possibly have. Yeah, exactly.
But for normal communication, just open an endpoint that happens to differ from the process itself.
Yes, exactly. And the gateway is certainly doing that in our model. Okay, and we think this is a usability improvement over some of the other diffC systems out there. And if you looked at Asbestos, for instance, that's really a message passing OS that's also implementing diffC policies, but really there were no reliable channels whatsoever in that system. And there are other really cool systems like HiStar, in which there's a low-level set of diffC primitives and a Unix layer on top, but that makes it pretty challenging for the programmers working at the Unix level to actually configure what policies they want in terms of these lower level kernel abstractions. So we figure this is a pretty important usability idea for getting these systems to actually run real applications. Okay, I'll briefly touch on the implementation. We're not going to. Sure.
So you told me that the declassification privilege you get when you create a new tag. That's cool, but in real life, Alice is going to persist over longer than the gateway process that created her.
Okay.
And how do you load those things?
Okay.
You don't create a new tag?
Okay, that's a great question. So really what we've built is we built a system where you could have a whole cluster of these things, all sharing the same ideas of what tags are. So when you really create a tag, what happens is the OS might actually make a call into some kind of Yellow Pages type service that's actually going to allocate that tag for the whole cluster. And then also in that Yellow Pages service, you can make a persistent token that you would attach to the tag as well. So in the case of the web application, it'll create a new tag. It'll be Alice. It'll say, OK, Yellow Pages, please give me a persistent token that I could use to recover this tag later. It'll then send that token to the browser as a cookie. And then the next time the browser makes a HTTP request back to the gateway, it'll send the token. The gateway will get the token, send it to the Yellow Pages. It'll get back the capability, and then it'll have the ability to declassify. When she flushes her cookie, she's got to log in again. And so with the login procedure, all right, now I have to describe the login procedure, which I don't know if I'm going to get right. But I think roughly the login procedure has Alice's password, her username, and another token that's a more important token because it's her rights to all of her privileges ever on the system. And so you could probably squirrel that away in a more trusted component that's in charge of login, where you give it a hash of Alice's password, and it gives you back all of Alice's privileges. And then the gateway process can take those privileges and exchange it for this temporary cookie as well. So the distinction between the temporary cookie and the more persistent login privileges is just one to better give us protection against break-ins in different parts of the system.
The answer to this is when you create the declassification privilege, it gets bound to a username that the login process.
Yeah.
Will hand back to you.
Right. And you could add arbitrarily complicated authentication mechanisms here. We've just done the simplest thing, which is just a 64-bit cryptographic token is enough to get back a capability from this Yellow Pages service. But if you want, you could use any sort of more interesting crypto to do it as well.
Login process, how do you know you trust?
You had to get it. You had to get it right. Is the answer. But the login process, it has a more restricted API than the gateway, right? So the login process is sure.
Set UID to root the process?
Yes, we do have an idea of set UID is another thing as well, and that is if you run this code, I'm willing to give you this capability, this privilege as you run this code. So we do have that concept as well. I think it's pretty hard to get around that if you want things to start up with privilege. Yes.
So the model I should have is that the things that go in your red oval, the gateway oval, are the gateway is just this router, but then also login, account creation, and the I guess the lookup, which I guess is login. The Yellow Pages is the login.
Yeah, exactly.
Store.
It's true. I mean, those are parts.
I'm trying to understand what you're saying is those pieces all belong in that red oval.
Absolutely. Absolutely.
I have one more.
Yeah.
Which is, if you're really building Facebook about this, some of the stuff you want to be secret, but some of the stuff you really do want to publish.
Right.
Right. I mean, it's a Facebook.
Absolutely.
Right? So are you going to have to put the really sort of detailed differentiation in, security policies of figuring out that this is the piece of Alice's page that she wants published, and this is the the embarrassing pictures that she doesn't want her future employer to find.
Yeah.
Is the knowledge of that going to have to be in the gateway?
I think we'll cover this a little later in the talk. It won't be exactly answering all your questions, but let's do that, and then we'll come back. Okay. So I'll tell you a little bit about the implementation. It'll take a couple minutes. So we haven't actually built a real kernel. I was lying about that. We've made an interposition layer on top of an existing kernel. And so what happens is, if you can imagine some web application that used to use glibc to call into the kernel, we've just replaced it with our version of this new system called Flume. We have our version of Flume libc, what that's doing is that whenever this application makes an open call, it just redirects it to a user space process called the reference monitor, which is going to issue that system call on the process's behalf. And of course, we needed a little bit more mechanism here to make sure that the web application wasn't circumventing the library to make calls just using assembly instructions. So we've written a little Linux kernel module to implement that policy. It's a pretty small module. And one of the advantages of building it this way is that we've actually gotten it working on 2 different systems, Linux and OpenBSD. And of course, we're interested in as many other platforms as people are interested in talking about as well. And just to tell you where endpoints fit into the story here, we roughly have endpoints corresponding to things like file handles, signals receive, signal send, child, exit, parent, wait, network, system 5, IPC, et cetera. So we're able to just use this abstraction of endpoints to cover a lot of the communication channels on Unix. All right, so let's start talking about a real web application to figure out how these pieces work in practice. Yes? So fork is somewhat tricky, but the answer is yes. The thing you have to really worry about fork, and we've just implemented it, we didn't actually implement it in an original paper. We implemented spawn, which is, please create for me this new, okay. But fork, you have to worry about shared file descriptors. If one guy, if the parent and the child both share a file descriptor, one could be reading from the file descriptor, and the other guy can say, where is the parent in the stream, and then that'll communicate information. So especially if one guy can change his label and the other guy can't, or sorry, one guy changes his label to read secret data, that's a good way to communicate data back to the child. So that was the thing we really had to worry about. And also, shared mmap regions are also a problem as well, but luckily, most processes do use mmap to load in their shared libraries. They don't use mmap in a way that allows communication between parent and child. So
even when they get separate file system tables, they're still actually sharing the file system data structure with the kernel.
Absolutely. So
duplicating all of them on the fly?
No, we're just saying you can fork, but you better have 0 file descriptors open. Which is no, it's certainly true. Yeah. So okay. Let me get this right. So one thing you want to share over a fork is a pipe, right? That's a very common thing to do. In our system, the way to do that, the parent calls make me a new pipe. It gets back a file descriptor and a token. What it then does is it forks. As it forks, it tells the kernel to close one end of the file descriptor. It shows up with 0 file descriptors open, it exchanges the token for a file descriptor, and then it has the socket back to the parent. Close them, and you have tokens that allow you to get new ones. There might be other ways to do this, but this was the way we decided to do it with making minimal invasions into the kernel. And fork is mainly a performance improvement that, as I described to you, our application, our real bottleneck is spawning new Pythons because they do so many system calls in startup. So fork would allow us to spawn one Python and just keep forking it a million times as new requests come in. Okay, so here's our example application. It's this program called MoMowiki, which a lot of people use on the web today to share data in some corporate settings, some public settings. And what happens is a lot of times these MoMowiki installations are encouraged to make their own plugins. So you can use MoMowiki in more of a corporate setting to enforce all sorts of interesting corporate security policies. Alice might be able to see her data. There might be group readable files like the layoff plans in some corporation where Alice and the security guard can see them, and there might be some public files that everyone on the system can see. And MoMowiki is trusted by whoever's running MoMowiki to get these policies right. And so the threat model we're willing to consider in terms of this program is going to look a little bit different from what you might be considering. And here's what it is. All the stuff in orange is going to be trusted. So we're trusting that the Linux kernel is correct, that some version of the Steve library is correct, that our Flume implementation is correct. And we're just assuming that all the stuff in blue is going to be vulnerable. Yeah, we can easily move Apache out of there. We just decide not to. I'm sorry? We decide not to re-implement Apache, but we're using Apache basically off the shelf in this case. And so the reason why you might think this is a bad idea is if you scale that hamburger diagram by the number of lines of code, you'll see that by far the biggest problem is Linux, and our little measly web application is not even showing up. But I would argue that as someone who's had experience with websites in the past, I'm much more concerned about bugs in the code that I only see and the code the summer intern in my company is writing, and not something that if there's a bug in it, Linux will patch the next day. So for instance, if you scale the area of the lines of code divided by the number of people who install this application, you'd wind up with a diagram that looks a lot more like this, where really what matters are things like the plugins and your application MoMowiki that is popular, but nowhere as popular as a Linux kernel. And by the way, if you think about all those attacks that I showed you in the first slide, I think most of them, in fact, probably all of them fit into bugs in the application, not that somebody hacked into Linux and used that to steal data. It could be that those people, that the hackers who steal data by bugs in Linux are just not sharing the fact they've done that. But in my yeah, because they're more of the pros. But I think a lot of security problems are from application level bugs. And so here's our implementation strategy for using this trust model in a way that's going to get us a better application. We're going to stick MoMowiki, the Python interpreter that runs MoMowiki, and all the plugins into this box that used to say web application. And we're going to stick the off-the-shelf Apache server and our little gateway process into this box called gateway. And it turns out that the gateway is about 1,000 lines of code, and MoMowiki is about 90,000. So we've managed to shrink the trusted part of the application a lot in doing this. And so what happens is when Alice comes to the website, she's going to make a request from Apache. Apache's going to fork a new version of our gateway, which is going to fork or spawn a new version of the MoMowiki process, which is going to implement whatever it had to do to show Alice the page she wanted. And of course, this gateway is running with all these declassification privileges, as I've described to you earlier. And all the stuff in red is going to be the part that we have to get right in order for the system to work. And the stuff in blue is going to be the untrusted thing that if there are bugs in it, we should be safe. So what are the results of this exercise? Well, the first thing we wanted to do is test this idea of endpoints in our implementation strategy to see if it was actually possible for non-experts, i.e. the people who wrote MoMowiki, to use our ideas and primitives. And we found that we had to make very few changes to the MoMowiki application in order to get this working. So we had to change about 1,000 out of the 90,000 lines of MoMowiki, and all the other stuff on the system was unchanged, like the Python interpreter, Apache.
Apache was unchanged because you trusted it.
Yeah.
That's partly.
Right, but we didn't have to rewrite it. We didn't have to recompile it even.
Yeah, I know, because you trusted it.
Sure. But what I'm saying is we didn't have to change the whole software stack to get this working.
Right. It's okay.
The denominator on this slide right here?
You see the line there?
Sorry.
It's not. We're just getting hurt.
Okay, no, it's fine. I would like to laugh too, but I don't get it. That's all right. Tell me later.
John is mentally.
Oh.
There's a division line between those two bullet points.
Oh.
Trusted and
1,000 is on the top,
dividing
1,000 is on the bottom.
Oh.
Along with Python.
But wait. I'm not there yet. Maybe I'll answer some of these questions in a little bit. But
I'm curious about how you found the code that needed to be modified. Can you characterize these?
Oh yeah, because you'd load the page and it would either be blank because the Python interpreter threw a stack frame, stack exception. It threw an exception, or it wouldn't show you the information you needed. And so a lot of these changes for the form, I'm about to read a file. Please stat the file to see what the labels are, then change the process label, and then read the file. So that was a lot of the changes we made. The other changes we made had to do with integrity, which I haven't talked about at all. So for secrecy, the changes were probably smaller. And are there more questions, or should I go on to performance? Yeah.
So MoMowiki can read Alice and Bob's data, right? And then send it out. And then because the gateway is sets are equal, it can take A or B as a result of the request that comes in. So how do you know that MoMowiki isn't rewriting Alice's data in its application contains Bob data, that contains Bob's data, and sending it out?
Well, it works in the same way on the way in. So on the way in, the data is coming from Alice's browser. It has the tag A on it. And then that means whatever Alice thought she was typing in, it's going into a file that has the tag A on it. And so on the way back, the same property is going to be.
You're not examining inside the application any information flow control, right? So you
No.
can read an Alice and MoMowiki is a long-running application, so you could have read in both Alice and Bob's files.
No, it's not a laundering application.
Oh,
It
it's
doesn't-
fine. I'm sorry.
It doesn't have any privileges, so it's hands are tied. what Moimon could do is Alice could say, fire Bob on the 10th, and Moimon could just write fire Charlie on the 10th, and that's a problem of integrity that is not discussed at all in this talk, but we talk about it in the paper. It's interesting, but I don't have time.
You can happily go off and acquire Bob's tag and write a file that's got Alice and Bob.
Absolutely.
It's just that the data would never get back off the machine.
That's
because it
totally.
would never get declassified.
Thank you.
Yeah.
Do you want to finish it up? Okay. All right. Let me tell you a little bit about performance. This certainly slowed things down in our implementation. And we're not even talking about a fast CGI version of Moimon. We're just talking about the old CGI model in which one process per request. And because we have the system call interposition layer, we're making about a 43% slowdown in reads and a 34% slowdown in writes. It's just going to be based on the number of system calls that the particular request happened to trigger. However, if you wanted to run this application, yeah, each system call is mapped to about 10 system calls. Yeah, if you put in the kernel, a lot of these problems go away. What's a little bit more tricky is getting fast CGI working, because that's really built on this Unix model of forking in such a way where it's OK to fork and share a file descriptor across a fork, let's say. We haven't actually done the work, but I think we could speed that up a lot too to get a fast CGI implementation working as well. But it's future work. And also, we can allow a cluster of servers, so if you really cared about this, we can scale linearly with the number of servers that are actually running the system, and they're all sharing files over NFS. Which one? Oh, no, this is by measurement. We ran it with 4 so VMs, and we saw a nice line. So it's by measurement. It's just based on the system calls that those particular types of processes, requests on Moimon tend to generate. I think the read request just generates more system calls. Is my best answer. So what are the security improvements? So there are 2 different 1,000 lines of code here. 1,000 lines of code we have to actually change Moimon just to get it working. But there's another 1,000 lines of code, and that is the code we stuck into this declassifier. And that's about 1/90th the size of Moimon, and what we're saying is that we're now just susceptible at the application level to bugs in that declassifier. And we actually were able to test this theory with 2 bugs that we found in Moimon that were in the version of Moin that we had inherited from the developers that carried through to our version that we had forked for this project. And let me show you one of them. It has to do with this feature called month calendar in Moimon. That you could write this in the Moimon syntax, some nice little one-line thing. It would generate this great calendar about what's going on in the month of March in this corporation. And it turned out if you moused over a date that had an event actually registered, Moimon would be more than happy to show you what was going on inside that day, even if the access controls shouldn't have allowed that. And so what happened is we ran the same thing using our version of Moimon, and we just got an output that looked like this. We didn't know the bug existed, but it just was refusing to show that data.
You could easily imagine it would do.
Right. I think it didn't crash actually after. I think the first time we ran it, it crashed. But it certainly didn't show the data.
Why didn't it crash? Second time around?
Why didn't it crash the second time around? I think, so I actually, it really depends on how this is implemented as an AJAX call or not. Yeah. So what the crash is that it tried to read data, wasn't allowed to, and the thing just, doesn't go any further. But I really should know the answer to this, but I don't. Yeah, I'll have to get back to you on that. I think this is an AJAX call actually. So I think this is what you get, but I should figure that out more. Okay. So there are other bugs that failed as well that were in the original version of Moimon that didn't work in our port of it. That the bugs just were not able to steal data. It turns out if you try to use any sort of related bug finding technique that's one of your favorites in this list, like, I don't know, taint tracking or software fault isolation, they would not have they would not have found this type of bug because in this case, the Python interpreter is acting exactly the way it should. It's executing all the right data. It's not jumping off the stack somewhere. It's just not implementing the correct policy. So it's pretty clear if you want to solve these types of problems, you're going to have to use some system where you understand how the application is moving data around and are able to interpose on that. So I'm now going to generalize and say why these ideas are more interesting than just this MoMowiki application. And it's a pretty easy step from here. Roughly, if you can imagine this setup that we had before, it's really just a black box in terms of security. That anything could have been going on inside that black box and not have affected security properties of the system. So what happens if we replace that black box with just totally unvetted, suspect uploaded code? And if you think about building a website this way, it's a totally new model. And what I mean by that is that here's some web application, potentially like Facebook, that has all these great features like photo sharing, blogs, or whatever else. And these have all been uploaded by third-party application developers directly onto our website. And as long as this gateway process is doing the right thing, then the security policies should be able to protect these guys prevent these guys from stealing data. And this is a new proposal called W5 that we're now working on building at MIT. And there's some things that have come up previously as to how to build a real social networking application with this. And one of the things to think about is how to share data. So you can imagine somebody like Chuck, who's a friend of Alice, who wants to see Alice's photo. Seems like a very reasonable thing to do. But what's going to happen when that runs? Well, Alice's photo has a tag of A on it. This photo sharing application also has a tag of A on it, a label of A on it to read the data. And then it has to send data out to Chuck. So what it does instead of going to the gateway is it first goes through this process called a declassifier, which Alice has uploaded onto the server or potentially chosen on the server to disclose her data properly. And it's going to run with her declassification tag. And so what that means is it can remove the, yeah.
Sorry? Yeah, that's where I was going to go. Is that from Alice's point of view, this is still, do you trust photo sharing?
Yes, absolutely. So Alice, one slide. Alice said this declassifier can see her data. She gave it this declassification privilege, and now the secrecy label can change from A to C, and it can send Chuck's data out to Chuck. I think the key idea here is that the data is opaque. What really matters is the label on the data. So this declassifier said something is trying to send me Alice's data, and I got to relabel it to go out to Chuck. It'll look inside this internal table to say that Alice and Chuck are friends. I should allow that. So if you think about what Alice is trusting in this system, she's trusting that the platform is correct. She's trusting the gateway is correct. And she's also trusting that the declassifier is doing the right thing. However, what she isn't trusting is all the other types of applications that she's running. Because as long as they're sending data out, and the data has to go through a declassifier to get out to Chuck, it's really just one piece of code as opposed to this ever-expanding set of applications that need to be correct. So I agree the problem hasn't gone away. It's just, again, been simplified in such a way that potentially we can get right. The code's malicious, all bets are off. So Alice has to know, she has to make one security decision. Which declassifier should I trust? Is it the friend of a friend declassifier that the people who built this website think is a great idea that the Microsoft Corporation wrote? Or is it every third-party application that I ever run, do I need to trust that? And so
that only works if Alice's declassifier isn't the application. If the application is something where Alice, it gives you knobs where Alice says, I want to share this one with Charlie and that one with Bob. At that point, the declassifier is now application specific. Okay. And now you're back to Alice saying, yes, I trust this one.
No. So that's how you upload data onto the system, right? So what you're talking about is Alice wants to upload a photograph. What tag does she apply to the photograph? And obviously, she doesn't have just one tag, the Alice tag. She has 10 different tags, like Alice friends, Alice family, just Alice, or everyone. And so another piece of this code is, if you really want to get into all the details of this, the way we're building it now is this gateway, when it shows you the page, there's actually something like a toolbar, more or less. It says, when I run this uploader on the software, which label should I apply to the uploader? And if the toolbar is trusted and it applies the right label on the data, once Alice's data gets onto the file server, it'll have the right tag on it, and then the declassifier can then decide to strip that tag off depending on where it's going to. Does that make sense? It's certainly getting more into it's certainly getting more into the details of the system.
So really these tags aren't principals, they're groups, they're permission groups.
Yeah, they're flat. They can refer to anything.
But the way that you use them is, the tag isn't I am Alice. The tag is I want this I'm Alice and I want this to be readable by this set of
Absolutely.
6 people.
Yep.
I can even change the set by changing the name classifiers rules on the fly.
Absolutely. Yeah, and we use that same policy in MoMowiki to do group readable, writable files. Yeah. Okay.
Has to know about Chuck, right? I mean, this same policy exists in like live spaces. It says, well, you can restrict my live spaces site to these people, but they have to have live IDs. So the default policy for most people say, well, allow everyone to see all my stuff because I can't convince all the people I care about my data to get a live ID when they have a live ID. It's just.
But Facebook shows that people actually do care about this, and they do try to get it right when they have the right knobs. You know, I think people really don't want their parents to see the photographs of the party they went to this last weekend, and that's why Facebook is so popular.
Exclusion, yeah, everyone has to join Facebook too.
Right. Oh, I totally agree. So we're assuming that Facebook, you know, they don't like this model because, you know, some new company showed up that built this, and they're going to eventually take over and provide all the same features Facebook is providing, but written by these magical third-party developers, as opposed to, you know, the people paid to write Facebook. It's kind of a pie-in-the-sky model, but it's a way you would do it with a totally different way of building the system with different security properties. More questions? No? I saw no hand? Okay. Anyway, so the idea here is that there were two previously distinct problems. One was that the server could be buggy, and the other is that there was malware, and these applications might be malicious. And I think we have the same mechanism in both cases to handle them. There's this idea of decentralized information flow control. And so in the future, we're going to really try to build the system up. And with this main idea being that what we really care about is not so much the OS we're building on, but we really want to build these new types of applications with this correct layer of the API to expose to the web applications. And I think a good place to potentially build stuff like this is maybe even in like a runtime in which you have different, it doesn't even have to be at the OS level. The same ideas can happen, something like at the CLR, if you think about different places to build this to get a web application up and going. Yeah.
So I'm curious about your thoughts about Michael Francis group that actually at the level of JVM, where they use similar tags, they use tagging controllable files, similar to the way you do.
Okay, I don't know this work. You're not talking about the GIF work, are you? No. Okay, then I'm not aware of it, but I should be. Is it here at MSR?
No, it's Michael Francis University of California, Irvine.
At UC Irvine? Okay. Let's talk about that. No? The GIF stuff? Okay, so Swift is going after a different problem, but the GIF stuff is potentially more. There was another GIF paper which tried to build web applications with GIF, which is called SIF, S-I-F. And that assumes a model where everybody is writing all their code in one statically typed language. And it happens that it's a little bit challenging to write in that language too. You have to write a lot more annotations for every variable you'll ever declare, and it's hard. It's a really cool system, and I think a good interaction between something like GIF and something like what we're building is that GIF would be a great place to implement all these declassifiers, let's say. So we have a gateway. We're making all these security properties that we're just assuming it upholds, but maybe we can throw some of the static techniques at the important parts of our system to get better security of just those components. Yeah.
Could you talk about the experience of writing MoMowiki plugins when the system is enabled?
Okay, so I can talk about the policies we have. I'm not the one who wrote the MoMowiki plugin, so I have to say my familiarity with the exact code is not. I spend most of my time working on this. But as for the MoMowiki plugins, I can tell you about the policies, the integrity policies that we've implemented, but that's not going to answer your question. So.
I guess I'm trying to get at the sort of overhead and the amount of thinking that has to go into writing such a plugin or a Facebook application for that matter, as opposed to a baseline.
How much you have to know about the underlying label mechanics? It certainly have to change the way you think. We're not able to drop in and magically change all the words from. The extent is, I mean, as I said, I really haven't spent much time. I mean, one of my co-authors, Alex, has done almost all this work. So, he's the one who who showed me the month calendar thing, which is why I didn't have the exact right answer for you. But I agree. I should give you a better answer. I don't have it. Anyway, I'm just going to conclude right now. And so the three important things we hit is, first of all, we had this idea for how to do end-to-end security on the server. It didn't include the clients, as was pointed out. But to realize this, we've had to build a new OS technology, which was influenced by a lot of the Mac work from the 70s, but has been changed in such a way to accommodate these new web settings. We call this decentralized information flow control. And I showed you more or less the API advances that we had to get this working. We showed an implementation and also an application that actually is running with the system that looks pretty similar to the application that we started out with. And finally, if you think this is a right way to be thinking about the way to build web applications, I think this could be really, we could use the same type of technique to apply to these interesting, dynamically changeable web apps that are coming up today. And so we think that's a good direction to push this stuff in the future. And with that, I think I'll take a lot more questions.
So with the W5 thing, it seems to me that one potential pitfall there is if you take random code and you download it in, you've just greatly expanded the attack surface, because now, as opposed to attacking with packets you can send to Apache, now you're attacking with any call you can make on Linux. And I think part of the reason that you don't see a lot of exploits that go through bugs in Linux is probably not that Linux doesn't have bugs, although they might let us to believe that. I think it's more that it's harder to get at it because you have to go through one layer of indirection before you, and you've eliminated, basically you've cut out, I don't know, firewall sort of a level in there. And
that's true. However, I will say that some people are currently doing this type of stuff. If you think about Second Life, they have more or less this type of model where it's some high-level scripting language, but I think you're able to run your code directly on the server. So I agree those are all issues, and I think that's why I'm not saying this is dumb work. This is certainly just a new direction to think about. What I would worry most about is things like database performance draining code. And so if you figure all this stuff is accessing potentially one database among all these different applications, what's to prevent one guy from making a really, potentially not even malicious, but let's say malicious query that just locks up the database for everyone? And that might be a great channel to leak information. And so I think that's really the thing I would worry about most. Sorry?
You can close the thing to the point where it starts paging,
Yeah.
and then it's just toast.
Absolutely. So you have all the same resource exhaustion problems that you've always had, and hopefully there's been enough progress in operating system research over the last 30 years to potentially mitigate those problems. I could be wrong.
You don't run out of resources as easily.
Okay, well, that's certainly one. That's certainly one idea. I was going to say something else, but I forgot.
Actually, so when I was an undergraduate taking operating systems, my professor, nearly the only thing I remember from this was my professor told me that the solution to coming up with better paging algorithms is not to come up with better paging algorithms, it's to divide more memory.
Okay.
And that professor is Rick Rashid. So.
Right. The other thing I will say is that typically when there's an exploit in Linux that allows privilege escalation, those tend to be patched and identified pretty quickly. Like the VM splice thing was the last one. Yeah. These are the same types of things we're worried about, right? Different processes on the same machine. Absolutely. And so, the other thing is that we have a very strict system call interposition policy, the way I describe it, that all system calls are really going through this trusted third-party application level reference monitor. So that is going to solve a lot of, because people have proposed this idea just to solve the insecurity of the kernel interface issue, this solution. And so we've inherited all those properties where now you don't have the whole API, you really just have this read and write to a peer application. And of course the peer can get, that application can get all the same things wrong the kernel can get wrong, but potentially it's made the problem a little bit better. Which way should I go?
I was wondering if you could comment some on the motivation for allowing applications to read things that aren't currently in their secrecy label and that they can't declassify. I guess just intuitively it seems like if I can read something and then I can't tell anyone about it, Why did I read it?
This is exactly the way the system works. I mean, you think about the web application, it's reading Alice's data, it can't declassify it. And so,
So I guess my question is why is it the case that why is it structured such that that is late bound rather than early bound, right? Why don't I have to, go ahead.
so agreed. In some sense, we've just generalized the properties that are in the Mac system. So in the Mac system, you get one chance to make the decision. In ours, you get two. More or less, can it read it? In the real system, we also restrict what a process can even read in the first place. But so let's just say we have a restriction when it can read the thing and when it can disclose it. Right. And it just so happens a lot of stuff in systems happens in between those 2 points, in which you could do a lot of things like write temporary files, make a pipeline of different processes that all filter it. These are things that systems do. And the fact that we don't have to reason about those in terms of security, I think, frees us from a lot of the same analyses that previous solutions have had to make in order to yeah, well, the decentralized is more so that the application, that the gateway is able to declassify. If you look at the older Mac systems, you'd need either a kernel policy or potentially a human being to declassify information. But we're decentralizing the ability to declassify information to whoever allocates a tag, basically. So that allows even an untrusted application in the box I showed to make a new tag and potentially declassify some stuff with respect to that tag. And that might be a good idea depending on what the application actually wants to do. You might just want to have a temporary scratch file that doesn't want any other application to see. And we would certainly allow that to happen. There are more questions, I feel like. Yeah.
I'm curious about the granularity of tagging that you perform. In particular,
right.
There's an entire field of database security which focuses on, I don't know, securing things in of columns, individual records.
Uh-huh.
And it also strikes me that, at least in a small web application, having a backend database with data from multiple clients and users is much more common than it is to have files.
Right, so the MoMowiki application just uses files. A database we're happy to support. And I think that's where we plug in all the great work that's been done on row level. We could accommodate all that row level types of policies, but it just has to be done by someone who the application is trusting to apply those policies. I think we're just making general framework. I think in a granularity question, you could go from GIF all the way up to what we've done. This way tends to make it easier to do things like write Python scripts, which a lot of people tend to do when they're writing applications. Yes?
I hate to keep harping on this, but it seems to me that at least what you're working towards, where you can upload any code you want, that there's nothing really you can do. I'm finding it hard to believe that you can actually, on a general purpose operating system, restrict all the covert ways that two processes can talk to each other.
He's not right. He's not
right.
He's solving that problem.
But it's true. But this is a great point, that if we are going to allow, so one argument against covert channels ruining the MoMowiki application is that to do a covert channel right, you basically need a receiver, a listener, and a speaker. And it's unlikely in this case that there were two, because there's just that much more work for the developer to have subconsciously done as he was writing this bug. And in the case where you're actually uploading things that are fully malicious, then they could work all they want. They could be developed specifically for that reason. So I totally agree. It could be that covert channels are totally going to blow the system out of the water before it ever gets started. However, I think that we're really not doing much better with our current solutions, if you think about what Facebook is doing. And this is not just an issue for Facebook. It's an issue for, if you want to make a server-side database or server-side, spreadsheet, what happens if that spreadsheet wants to do something like call a third-party function? Figure this plugin idea for servers is going to really be catching on. And I don't know a better solution than what I've just described. I mean, clearly we have to start thinking about the data. As soon as you export the data to some third party, it's gone. I mean, that's one thing we know for sure. And so we're trying to make. Yeah, exactly. That's one way to answer the question. I hope it's sufficient.
Well, I was just wondering, are there any low-hanging fruit there? Not the really extreme cases like Bill was talking about timing the disk RMCs or something.
Right.
But there's a bunch of just regular system stuff you can do on most general purpose operating systems where you can name things, system objects, for example, and that are visible to other processes.
Absolutely. We have not explored any of that stuff. And there's been obviously a lot of great research in it. I think the answer is that if people are willing to give the system a chance, then we could start trying to go after all those other issues as well, including making a new database, potentially rewriting a database with diffc built in would be a really interesting project. I just don't think it's worth it unless people actually buy into the vision. So it's kind of like putting our toes in the water.
I mean, it sounds like all you kind of motivated with exfiltration. Exfiltration is really not the problem you're trying to solve, because you're really not worried about these covert channels. You're trying to make it harder for a programmer to screw themselves. Your real threat model is the calendar application. It's not a deliberate malicious, I'm going to read someone's bag.
But that's not the case in the W5
Yeah,
platform,
absolutely.
right? You are running my code, I can write any malicious
It's like
thing.
every other security thing that we've ever done, which is that it raises the bar, but it doesn't get it all right. Right? And you can't fault him for not having solved a problem that nobody else has been able to solve.
And notice there's a general problem. a conspicuous absence in this work. You don't make any concrete statement about whether P is or is not equal to NP.
With that, we can thank our speakers.
Well, thank you. Well, actually, I mean.